Okay, before we start, are there any questions from last time? Any questions on homework? So what we're going to do today is we're going to spend the first few minutes going over an example that will be helpful for this week's coming homework. It's going to pick up the X-ray imaging example from last time, and then we're going to spend the rest of the lecture today talking about Fourier transforms. And so for some of you, this will be an introduction. For those of you who've already had Fourier transforms, there'll probably be a little more emphasis on 2D Fourier transforms, which a lot of people don't feel comfortable with. So this will be the first introduction to that. We'll also cover Fourier transforms again when we talked about MRI and go into a little more detail. And obviously, throughout the course, we'll be using it. So this is really just the first introduction to give you enough basics such that when Professor McVeigh covers computed tomography, you'll have some basic information there to understand some of the theorems that he's going to use. Okay? So if there's no more questions, let's get started. So we're going to revisit this problem of this X-ray imaging thing where we have a source, and I've actually changed a few things. It's almost exactly the same as it was last time, but there are a few key differences which are going to be useful to make sure you understand for the homework assignment. So one is I've now got a factor of 2 in front of the source, so it's 2 times rect of x over 10. That just means the source is twice as strong. And now I have a factor of 3 in front of the transmittivity function, which means it lets 3 times as many X-rays through. Okay? So you should expect that the intensity at the detector should be overall a factor of 2 times 3 or 6 greater, right? You've got 2 times as many X-rays, your transmission function is 3 times as great. All right? So we're going to just basically, so for the homework, you're going to be asked to do convolution, but also do sort of a sanity check using sort of a diagram like this, just using geometry to check that your answer is correct. And that's a nice thing about medical imaging is that you have these built-in checks. You know, if your image doesn't look good, you know your answer is wrong. If the size of your image is the wrong size, you know you've made a mistake in the math. Okay? So you can use, often in this course, you can actually use these physical checks to make sure your math is correct. So let's say we want to figure out an intensity at this point. So at this point, we're at -5. Okay? And we're asking how many X-rays make it through to that point. And what I've shown you is I've drawn you sort of the span of all the X-rays that make it through that point. Okay? So basically, all the X-rays from the source can make it through the transmission function to that point. All right? So we ask what the intensity of X-rays is. Well, any one X-ray has an intensity of 2 times 3, right? It's got intensity of 2, transmission function of 3. So there'll be a factor of 6. That one single X-ray alone has a factor of sort of intensity of 6 coming through to hit the detector. Okay? But now we have this distance here is 10. Okay? So if we think about each little incremental, so it's actually more like each X-ray actually doesn't give 6. It actually gives 6 times some dx. Okay? Some little differential part of the source. Okay? But since it's uniform, we can simply think about integrating that over this whole source, right? Think of all the X-rays, each with a 6 times dx contribution. Since it's uniform, all we have to do is multiply by 10, right? Which is the width there. So then what we could say is the intensity here is 10, or 60, sorry, 60. So 6 times 10 equals 60. All right? So that's the intensity of the X-rays that hit the source. And in fact, if I look at any region from here to here, from -5 to 5, you can sort of convince yourself, since it's symmetric, that anywhere in that region, if I move my dot anywhere in that region, all the X-rays can make it through. So over that region from -5 to 5, I'm going to have an intensity of 60. Okay? Does that make sense? All right. So we can start drawing sort of our answer. So we know that, let's say, from 0, -5 to 5, we know from here to here, my answer is going to be 60. All right? So without even doing any sort of convolution, you can just write the answer down by inspection. All right? So now let's go off to this point here. So now we're off at, I think this is -10. Okay? So I've gone a little farther off. And then this is going to be -15, I believe. Okay? So now how many X-rays are getting through? About what fraction of X-rays are getting through now? Half of them are getting through, right? So only half are getting through, so we expect the intensity to go down by a factor of 2. So we know the intensity at this point is going to be 30. Okay, and it's going to be symmetric, so we can go back to our picture, and let's say we write minus 10, 10. We know it's going to be 30 at these points. Okay, so and we can sort of assume it's going to be a linear decrease like that. All right, you can sort of think about as you sort of just move off, it's going to just sort of the fraction of X-rays that can make it through just linearly decreases. All right, now let's look at here. How many X-rays get through here? So I'm now at minus 15. Right? So basically no X-rays get through, right? It's 6 times dx, but if dx is infinitesimally small, it's basically 0. Okay? So we know that here the intensity is just going to be 0. All right? So we can go back to our graph here and write minus 15, 15, and it's go down to 0 at that point. All right? So that's what we'd expect to get if we do the convolution. All right, so that's sort of a nice sanity check. So we're doing it in reverse. We're not doing the math first, we're doing the physics first, okay? But now let's do the math, okay? So what we had is that the math should satisfy this, right? 1 over m, s of x over m convolved with t of x over m. All right? So let's see if that works out. So we have that given that z equals d over 2, little m equals 1. There's actually a minus sign, but everything's symmetric, so I'll drop it for now. And big M equals 2. Okay? So we have exactly what we had last lecture. We have this rect of x over 10, so that's my scaled source. And I have rect of x over 20, which is my scaled object. And then I have these factors of 2 and 3 now. Okay? So that's the only thing. Those factors of 2 and 3 are the only thing different today from last time. All right. So let's actually go through sort of the mechanics of how you would think about doing this as a convolution, okay? And see if we get the same answer. Okay. So what I've shown you here is basically this is the physics side here, and now we're going to do the math side, okay? So here is my rect of x over 10 here with a factor of 2, okay? So that's just this thing here, okay? And this is my rect of x shifted x plus 5 over 20 with a factor of 3. Okay, so I've shifted it to the left by 5 because I want to know what the answer is at x minus 5. Okay, question?
Why is it rect x over 20 instead of 10?
Okay, so this is the transmission function over big M. And so since that was rect of x over 10, since big M is 2, it just becomes 20. Okay? All right. Good question. So this is shifted over by 5 from what it was symmetrically, okay? So this is just shifted over by 5 because I want to go minus 5 direction, okay? So now if we think about the overlap, it's only going to overlap in this region here, right? That's the only region of overlap of those two rect functions. And that region of overlap goes from minus 5 to 5. Everywhere it's 2 times 3, so that gives you 6. Okay? So what's the area of that overlap? Just 60, right? Which is good because that's what we got from the physics. All right? So it's a nice sanity check. All right. Now we're going to shift over. So this is now 3 rect of x plus 10 over 20. Okay? And now you see the area of overlap is less, right? Okay. So this area of overlap has a width of 5. The height is 6. So what's the area? It's just 30, right? Okay. So that's good because that's what we matched. So this is at x equals minus 5. This is at x equals minus 10. And now we're at x equals minus 15. And so here we have 3 rect x plus 15 over 20. And there's basically no area of overlap. Okay? And so the answer here, so there's nothing to integrate, the answer is 0. All right? So that's really sort of how, so that's doing it the convolution way, which is just pure math, and we're just showing that it gives you exactly the same answer as if you do it using geometry. All right? So on your homework, there'll be a problem similar to this. Okay? Almost, it'll be like 20%. It'll be, if you know how to do this, then the homework should be fairly straightforward. So if you have any questions, just ask either now or in office hours. All right, so that's all we're going to do for now with X-rays. You'll pick up again next week with Professor McVeigh when we talk about CT. But for now, we're going to change gears a little bit and provide everyone with a little bit of background information on Fourier transforms. All right. So far, we've already talked about, let me just move this so it goes away. We've talked about representing signals as Dirac delta functions, okay? And so we said that any signal can be represented as a sum or an integral of weighted Dirac delta functions, weighted and shifted. So that's one way to represent signals. But the other way that's prevalent throughout all of science and engineering is Fourier transforms, which is representing signals as sums of sinusoids. So you've probably seen this before in a physics class or something. So imagine you've got, well, no one has a radio anymore, but if you did have a radio, it would basically receive signals from the transmitter, and you might get a signal like this on your radio. Okay? And your radio antenna picks up different frequencies. And so, for example, if these were the 3 different stations that were transmitting, each one is at a different frequency. Okay? Each one, depending on how far you're away from the tower, you're going to give a different amplitude. So these sum up to give you that. Okay, so the sum of all those 3 signals is that signal. Okay, so the conventional way of describing that signal is describing its value at every point, right? So I could imagine telling you the value of this at every point, and you might see I might need 60 numbers or some number of numbers greater than 1 or 3 to represent that in time domain. Okay, so this is a function of time, let's say. But if I knew these were the only 3 stations and I knew their frequencies, then really all I need is sort of these 3 numbers to represent what's going on, right? I just need to tell you the amplitude of each of these sinusoids, and you can fully describe what's going on, because you could just take these frequencies, multiply them by these amplitudes. So these are like the amplitudes. And so that would be a much more compact description of your signal. All right. So this is basically a specific example of going to another basis function. You're representing your signal in another basis function. So all of us use this every day because the reason we can watch YouTube is because the videos are converted into wavelets or JPEG, different basis functions. I think right now it's more wavelet based, but before it was cosines. And so basically that allows them to transmit the information with much less numbers. Okay? If they had to transmit it pixel by pixel, we'd all just be waiting for our videos. All right? Okay, so let's talk a little bit about, so in 1D it's pretty easy to sort of think about just sinusoids adding up. Okay? Because the only thing you have is you have the frequency of the sinusoids and their amplitude. For 2D, the thing is it starts to get it takes a little more time to sort of think about what frequency is, and so these are examples of different spatial frequencies. Okay? And essentially, it's basically a spatial frequency is how rapidly does your image vary with space. Okay? So you can sort of see in this top row, as I go from here to here, obviously my spatial frequency is increasing. Right? Things are changing faster in space. All right? But the other sort of degree of freedom we have is what's the angle of the variation. Right? It's not just, images aren't just made of things varying left to right and up and down. They can vary at all different angles. All right? So this is an example here where the angle of variation is varying as I go from here to here. Okay? And so we want to start thinking about imagining that any image can be represented as a sum of these sort of zebra stripe patterns where the spacing can vary, but also the angle can vary. All right? So that representation is saying that I can be an image space here, where I view my image in the conventional fashion, where I have to tell you the number, the intensity of the image at every point. Or I could describe this image in what's called Fourier space or K-space. Okay? So especially in MRI, the term K-space is used quite frequently. And in physics, you might have heard of K vectors and things like that. All right? So the notation we use is that, let's say this is x and this is y. Okay, those are the coordinates in my image space. In my K-space, I'm going to use K sub x and K sub y. Okay. Now the book uses u and v for some reason I don't understand. Okay. I do MRI and everything in MRI is kx and ky. So, but there are fields where they might use u and v. So you're just going to have to get used to that. So in this class, the book will use u and v, but we'll use kx and ky simply because in medical imaging, that's pretty much what I see being used. And so if you're going to go out there and read the literature, you're going to see a lot of kx and ky. All right. Okay, so let's go through and talk about how to interpret K-space. So we're going to spend a few minutes talking about this and then give you guys some examples to work on to make sure you understand what K-space is. Okay, so this is basically K-space representation of a signal. This is Kx and Ky. And essentially the intensity, every point in this K-space representation is saying how much energy is there at that spatial frequency. So we want to interpret we want to start understanding what different parts of K-space represent. All right. So here is sort of, let's say I have some case, I want to look at the K-space intensity at this point here. Okay. So that is off on the Kx axis. Okay. So anything that's right on the Kx axis, that intensity represents variations that are going left to right. Okay. So that's how you think about that. So let's say this has some variation. So it might have some period. Let's say it has some period of, let's say, what's a good L. Okay. So then the Kx value is just 1 over that period, 1 over L. Okay. So that's the frequency. So this is the frequency. And then the L is the period or the spacing. All right. So I would expect that as I move farther out, if I move in this direction along the Kx axis, then as Kx gets bigger, that L has to get smaller. All right, and that's exactly what it is. So here I've moved out a little farther along the Kx axis, and you can sort of see this spacing here, L, has gotten smaller. All right, so that's basically anything along the Kx axis is pure left-right variations. All right. So similarly, if we go along the ky axis, so we're at this point here, then that's the L here is here, but now it's up-down variations. Okay? So anything along the ky axis represents variations going up and down. If I go farther out along there, you see this L gets smaller. Okay? So it's a higher spatial frequency, so the period is less. Right? And then what happens if I go out in K-space like here? Okay, that means it's going to have both up-down variations and right-to-left variations. And so that's an example here. So this is the variation that corresponds to this part in K-space. All right. And if I went farther out, let's say I went farther out and picked a point here, then I would just expect it to look, it'd have the same sort of angular thing, but it would be a much finer spacing. Okay. So in general, a good sort of rule of thumb to think about is if you're given any point in K-space, say Kx, Ky, and you draw the vector to that, okay, the spatial pattern that corresponds to is simply going to be the lines that are perpendicular to that. Okay, so that's how you can remember what the pattern should look like. Go to K-space, draw that vector, and then draw something perpendicular to that vector. That's going to tell you what the spatial pattern looks like. Yes, question?
What's the significance of always putting the negative quadrants as well?
Yeah, so that's a great question. So you notice that there's both positive and negative frequencies. There's a couple answers for that. One is it makes the math easier if we allow things to be positive and negative. Otherwise, you have to carry around cosines and sine terms, and it just allows us to use what we'll talk about in a few slides is exponential notation. So it cuts your work in half, at least in half, okay, if not more. And then actually when we get to MRI, it has a really cool interpretation. It actually has physical meaning. So wait for that answer, but for now, it just makes our life easier. Okay? Otherwise, you'd be writing twice as much math, which no one wants to do. All right? Okay. Okay, so so this is a slide showing how you might start creating an image from these Fourier components. And so what it's showing you is basically as you start off imagining, it's sort of like 3D printing. You can imagine, this is examples like you're adding on each component and then creating your image. So you first start off with a component that looks like this, okay, which is very low frequency, right? And so this is the component and this is your image. And then you add on this one. So you're going to add this on, and now your image starts looking a little more circular. Now you add on this component, you start getting sort of this diagonal feature. You add on this component, it starts shaping up a little more. You add this component here, it looks like this. And you sort of keep adding components and you look at the resulting image. So I add this, it looks like that. I add this, I'm getting more and more detail until finally I actually have a fairly respectable image of my brain. Okay, so the idea is any image can be made up of just layering, just summations of these components. All right. So what I'm going to do now is I'm going to play this movie. So let me just switch gears a little bit. Okay, so what you're seeing on left is the k-space representation, and then what you're seeing on the right is the image that results from that. So let me play that again. And just sort of, you want to sort of look at both the left and right together and sort of see what you see is going on. Okay, so I'm starting off at the center of k-space, which is low frequencies, and I'm going out further and further into higher parts of k-space. So what do you see going on? What's happening? Let's say we go here where there's not much, where we're only keeping a little the stuff near the center of k-space. Is this what do you sort of? How would you characterize this image? Is it clear? Is it blurry? Is this, yeah, it's blurry and it's got a lot of weird artifacts too, right? This is, hopefully your brain doesn't look like this, because if it did, it probably wouldn't work, okay? And so you can sort of see as we make that, as we start including more frequencies, we still have artifacts, but it's looking a little better. And as we add more and more frequencies, you know, we sort of fill in all those details. And at the end, when we've got all of k-space, we have a very nice looking image, okay? So this is showing us that the center of k-space is really sort of the rough details of your image, and then as you get more and more of k-space, you start filling in the details. Okay, so let's look at some examples of that. Okay, so this is the first example. So this is my image, and then this is its Fourier transform. Okay, and what I've done on this, so I'm going to take this Fourier transform and just for purpose of example, I'm going to just zero out all these areas. So I'm just like getting rid of the k-space information in those areas. And then I'm going to recreate the inverse Fourier transform. And what we can do is we can zoom in on this guy. So what do you notice about this image? It's pretty blurry, okay? But if you think about what are the edges that seem to be most blurred out? Are they the vertical edges or are they the horizontal edges that are most blurred out? Okay. So to ask the question, so let's say these are vertical edges. So something like this, are these edges blurred out or are edges like this blurred out more? Can you guys, especially look at this region here of the brain. Okay. So these ones here, right? These are more blurred out, right? Because if you imagine traversing like from here to there, you can sort of, those edges aren't that clear. But if I traverse this way, you can sort of see that those edges are still fairly sharp, okay? Which means I've sort of kept this information, but really sort of lost some of that information, okay? So now if we zoom back in, remember anything along kx corresponds to sort of vertical edges. So if I get rid of some of that information, I would expect those edges to be blurred or lost information. Okay, so there's always the sort of the problem is when we use this, these are vertical edges here, but they're sort of going left to right. So you sort of have to. Sometimes there's some confusion about what we mean. So you can just if you're explaining it to someone else, just go like this or like this. That's basically what you need to do. All right. Okay. So everyone got that example? Okay. So now let's play the same game. Here I've zeroed out this area. Okay. So let's zoom in on this. Okay. So now you notice if I traverse from here to here, those edges are pretty blurry now, right? So the edges like that are now blurry. Whereas going from here to here, it's still fairly sharp. Okay. So like for example, this boundary is pretty sharp, but this boundary here is pretty blurred out. Okay. Can everyone see that? Okay. So if we zoom in on that, you can sort of see sharp there, but blurred out there. Okay. So sharp, blurred. All right. Okay. So, and that makes sense because I've gotten rid of this sort of information, right? These components out here. Okay. Now if I zero out everything here, so everything out here is zeroed out, then you're sort of seeing everything is blurred in all directions. All right. Okay, I've lost the detail of anything going left, right, up, down, or even diagonally. All right. So that's basically sort of your first sort of passive K-space. Now let's assume that I zero out this stuff in the middle and I only keep this information here. Okay. So now let's look at the image. Okay. So you can sort of see I've kept this information, right? But I've lost the information going like that, right? So this whole area is like zeroed out, right? Because I don't have that information anymore. I only have information about edges going left to right, or these vertical edges, right? Because I've basically only kept this information. You see that? Okay. Similarly, if I only keep this information, let's look at what the image looks like. So now you see I've kept these edges, right? These are really nice edges there, but I'm sort of starting to lose these edges, right? These like here, there's none of that vertical edge that I saw before. Okay? And that makes sense because I'm only keeping sort of this sort of information. All right? Okay. And similarly, now I'm going to keep all this information out here. Okay, so I've got both these edges and these edges. So I'm only keeping the outer parts of K-space. And so now if we look at the image, we can zoom in on it. You see we've got nice edges this way, nice edges that way. This is a really cool area of the brain, the cerebellum, and you sort of see all those nice little edges there. Okay, that's the part of your brain responsible for the fact that you can walk and have motor control. Okay, so. All right, so that's that. And then let's look at one last example before I give you the in-class exercise. So now we're going to sort of take our Fourier transform and we're going to add on like an artifact. Okay, and this happens a lot. This can happen in, for example, an MRI where if there's any interference, it can just inject energy into the system, and that can end up, as we're going through K-space, it can just end up anywhere in K-space. Okay, so assume that I just had some energy injected at this point in K-space, right? So that's going to represent some variation going like up and down, right? And so you notice the resulting image, in fact, has your image, but it's also got this interference of stripes going up and down. Okay. Similarly, if I inject something there, if I think about drawing this arrow, it should inject stripes going this way, right? And lo and behold, I have stripes going that way here. All right, so that's about all you need to know to do the exercises. All right, so this is your first assignment here. So you go to pollev.com 280A. I'll post the poll in a minute. What I want you to do is work in groups, discuss this in groups. So the answer should be, put your names in brackets of whoever's in your group, and then for each one, your answer might be like, this isn't the answer. This is just, you'd like do B1, C2, D3. Basically, this goes to this, so you're just trying to match B through D with 1 through 3. Okay, so which of these things corresponds to the other? Everyone understand the assignment? Okay, so go ahead and discuss this with your neighbors, and I'll open the poll in a minute. Hey, Sean, can you hit preset 2? It'll just lower the light so they can see the image better. No, number 2, the one, no. Okay, go to the bottom, and then the one up on top. There, hit that one. Yeah. Yeah, that'll make it easier for them to see that. Okay, thanks. Feel free to, if you need to get closer, you can come up and look at it, or, yeah. Okay, about 1 more minute, so enter your answer in the next minute. Does it help if should I turn off these lights too?
No, we're talking about the air.
Oh, okay.
There's cool air that's going right here.
Okay, all right. Okay, let's take a look at this. So most people have submitted their answers, so that's good. And there's pretty good agreement between answers. There's a little bit of diversity, so let's talk about it. So let's assume we knew nothing and just had to figure out how to increase the odds of getting it right. Okay. So I have these 3 things on top, say B, C, and D, and I have the 3 things on the bottom, 1, 2, and 3. Okay. So out of B, C, and D, which one has the most detail or information of these three here? Yeah, D definitely has the most detail, right? Okay. And then of the 1, 2, and 3, which has the most number of white points or information? It's got to be, it's 1, right? Okay. That's the part has the least amount that's zeroed out in general, okay? So basically, even if we knew nothing, we could probably guess that D goes with 1. And then if we think about what we talked about, we know that this it's got information about these edges and information about these edges. And if we look at this guy here, it's definitely got edges this way and that way. Okay, so that's a good sanity check. All right. So now we've increased our chances, so we only have to decide between does B go with 2 or does B go with 3, right? So we look at this image, it's really got these edges going up and down, right? Much more than it has, it's sort of lost these edges going left to right, okay? So it's much stronger, so we would say that we've mostly kept the information going up and down. And so we go back to here, it's got to be 2, right? Because this has that sort of information. So B goes with 2, and then this has information about these sorts of edges. And if we look at the image, lo and behold, we've kept that information. Okay, so that's how you would look at that problem there. Any questions? Okay, great. Let's move on to your next exercise. Same thing, 1, 2, and 3, A, B, and C. Okay, go ahead and take a few minutes to look at that. I'll switch the poll.
If we go upward from the center, then the edges. We don't have this. We should have but that's what I said about the fact that we can copy things.
Okay, about 1 more minute. Submit your answer in the next minute. Okay, let's take a look at this. So there's pretty good agreement, although there is some diversity again. So As before, we can sort of think about which of the images on the bottom has the least amount of information. And just by looking at it, it's clearly A, right? And then in terms of the least amount of information on the top, it's 3. And so I think most people got this, okay? Where there was some sort of diversity was the remaining 2 answers. So you had a 50-50 chance of getting it right. So let's look at that. So this one here, if we zoom in on this image here, it's got these edges here like that preserved, right? And it's missing this sort of information, okay? So we want to see which of the Fourier transforms would preserve that sort of information. And it's going to be 1 because this has information along the kx axis, okay? So B will go with 1, all right? Does that make sense to everyone? Okay. So if you didn't get that answer, then think about it. And if you still have questions, please ask me because it's an important point to get. Okay. So let's double check on this one. So here, you know, once again, the edges are much stronger going up and down than they are in the other direction. So we want to look at the Fourier transform that preserves that, and it's going to be this one here. Okay. So then we verify that this goes with that. So everyone okay with that? Okay. So if you're okay with that, now you're ready for the hardest one, which is this one. Okay. You want to just can you dim the lights completely for this one, just so you, because this might be a little hard to see. Yeah. Okay, about 1 more minute, so submit your answer in the next minute. Okay, let's take a look at this. So people did pretty well, but I think this was definitely a harder problem. So even people who aced the first two had some issues with this one. Okay, so yeah, keep it low until we're done with this one, and then we'll yeah. So let's sort of play the game again. Out of 1, 2, 3, and 4, which has they're all images of the brain, and they all have interference on top of them, right? But which has the simplest interference? 1, right? It only has vertical stripes, right? So the 1 is the easiest one. Oops, what happened to my pen? Okay, so 1 is the easiest one. It's got stripes going like this. Okay, so which of these A, B, C, and D corresponds to purely vertical stripes? B, right? Because it's right on the kx axis, right? So it can only represent vertical stripes like that. Okay, so B does, I think most people got that one, so that's good. Okay, so now it becomes sort of like what looks like the other, okay? So it's going back to like Sesame Street. So which of these 2, 3, and 4 looks the most like 1? 3, yeah, so these are sort of the most similar, right? And then which of the A, C, and D looks most like B? C, right? So it's got this, so it's going to inherit these sort of vertical, but in addition, it's off diagonal, right? So we'd expect it to also have stripes like that, okay? And if we zoom in on this, we can sort of see there's these vertical stripes, but there's also these stripes like that. Everyone see that? Okay. So that means that C goes with 3. Okay? So now these guys here, A and D, look the same. They're just opposite sides of the spectrum. And so we can just imagine plotting, this is going to have stripes like this, and this is going to have stripes like that, right? So then we look and see which of those. So 2 has stripes going which way? This way, right? So we look down here. So 2 must go with D, right? And then we double check. A says it has stripes going that way. We zoom in on that, and it's got, lo and behold, it does have stripes going the right way. Okay? So everyone okay with that? Okay. So once you get the difference between up, down, and left, right, you're okay, right? But it's tricky. In images, it seems like a trivial matter, but oftentimes it's the matter of making sure you know what up, down versus left, right is, and which is left. In fact, actually, it's sort of funny, but even when people look at images, you're not always sure which is left and right, okay? Because it gets, neurologists and radiologists actually display their images differently. So left is left for one person, but it's right for another person. So sometimes we even have to go to extreme measures like put a vitamin E capsule on someone's head and tape it to their head, just so we know which is their right side of their head, because it's not always obvious. Okay, all right. And so this is sort of an interesting example because I mean you don't necessarily see these severe artifacts in MRI, but you actually will see things similar to this. And so if you ever get an MRI exam on yourself and you see stripes on it, you'll be able to tell what part of the case space was affected. Okay? So that's sort of cool. All right. Hopefully you don't get that, but if you do, then, and sometimes you'll be very faint. You'll just say, hey, what are these little stripes going through my brain? And that's because there was probably, it could even just be 2 wires that just sort of happened to contact each other for a millisecond or less and created some RF energy. All right. So are there any questions on this example before we move on? Okay. So now we're going to sort of start talking about math for a while, just because there is some basic stuff that we do need to cover. So let's first of all define the Fourier transform. We'll first of all do it in one dimension, then we'll talk about it in two dimensions. The sort of deceptive thing is that the Fourier transform, the definition is really simple, okay? And yet people have written books. I mean, when I was in grad school, I took a whole quarter just on Fourier transforms. So that wasn't even enough to cover what was in the book. So I mean, you could spend many, many years studying Fourier transforms or your whole career. We're just going to touch the surface today and give you the basics that you need to at least start understanding how it's used for medical imaging. All right. So the Fourier transform of some function g of t is simply you take g of t, you multiply it by this complex exponential where j equals the square root of -1, so it's the imaginary number. I'm an engineer, so I'm going to use j. If you're a mathematician, you would use I. But for electrical engineers, I stands for current, so we use j. Okay, so that's why there's i's and j's. All right. So in this case, it's e to the minus j 2 pi f stands for the frequency. In this case, it's temporal frequency. Yeah, if you could turn that, that's great. And so that we'd say that this is big G of little f is equal to the Fourier transform of g of t at that frequency of f. Okay. The other way you can write this is the Fourier transform operating on some function g of t. So you'll see all those different notations. All right. The really cool thing is once you have g of f, you can plug it into this equation. You multiply it by this, which is almost the same thing as what you had before. There's no minus sign. And then you integrate over df, and you get back your original function. So you can do the forward Fourier transform, and you can also do the inverse. And that's what makes it so powerful. And then we define that as f inverse g of f. Okay, so that's the basic notation. Let's talk about units. So when we talk about things in terms of time, like a speech waveform, typically t will be in seconds, f will be in cycles per second, or hertz. Okay, so those are the units. In this class, we'll be talking much more about spatial coordinates. So x might be in centimeters, and then kx would be the spatial frequency, which is then in cycles per centimeters. All right. So and the notation here is we'll typically use t and f if we're talking about time and temporal frequency. We'll use x and kx if we're talking about spatial frequency. All right, so that's just the convention we'll use. Okay, so I don't have to, I'm assuming everyone knows how to use complex numbers. If any of these things are confusing to you, just review it, okay? Once again, I assume everyone knows or has seen complex numbers, so this is just saying you should know, you're responsible for knowing this information, that you can represent a complex number as so. The magnitude is defined as follows, and the angle of the complex vector is as such. So that we also say z equals z e to the j, e to the plus j theta. So that's the other way we can represent our complex number. Okay? So we can either represent it as the components, the real and the imaginary, or we can represent it by its magnitude and its angle. Okay? And as you're seeing, we're actually going to use, these are going to be much more important for what we're talking about. Okay? The good thing is if I have something like e to the j theta, right, what is the magnitude of that? So what's the magnitude of e to the j theta? It's just equal to 1. Okay? So anytime you see that, the magnitude is just 1. And then so it's basically what we call, it's a phasor with magnitude of 1 and angle theta. Okay? Where this is the real and imaginary axes. Okay? And the reason, as we talked about with the previous question, the reason we do this is just makes the bookkeeping much simpler. Right? So there once, and then the other thing that's really important is to remember Euler's formula, which is just this interesting called e to the j theta. Amazingly, it equals cosine theta plus j sine theta. So everything fits together. So when I have an imaginary number, I have theta is its angle, and therefore the real part is just cosine theta, and the imaginary part is just sine theta, because it has a magnitude of 1. Okay? So this will become super useful when we talk about MRI, because actually, until I learned MRI, these phasors were just imaginary things. When we get to MRI, they're actually in your body. Okay? There are actually phasors doing this in your body. Okay? So that's really cool. Okay, so let's talk a little bit about the 1D Fourier transform in some more detail. So now we're in space, so x and kx. So if we apply Euler's theorem, we can break this into g of x cosine 2 pi kx dx minus j gx sine 2 pi kx dx. Okay, so basically, the one way to think about it, we'll present different ways of looking at this, but for today we're going to really focus on sort of saying, the Fourier transform is telling you how much your function sort of looks like a sinusoid or a cosine at that frequency. Okay, so if g of x looks like cosine 2 pi kx over x, then this integral will tend to have a large value. And if it doesn't look like that frequency, it will tend to have a lower value. Okay, and so you can sort of see that the nice thing about this notation here is we don't have to carry around the cosine and the sine around. Okay, we can just say carry around the complex exponential. So let's talk about how do you compute transforms. And we're not going to, in this class, we're not going to look at computing really gnarly transforms. We're just going to talk about some very simple transforms that are really important in medical imaging. Okay. The first one is the Fourier transform of the delta function, which is important because we know we're going to use a delta function to represent an impulse, and we know we need to look at impulse responses. So we just take delta of x in here, and remember delta of x from the sifting property just picks out the value of the function at wherever the delta function is active. So this is active at 0, right? This only has value at 0. So it's going to pick out the value at e to the minus j 2 pi kx times 0, which is just e to the 0, so that's just 1. Okay? So the nice thing is, and typically what we'll say is a delta function goes to 1, okay, in terms of its Fourier transform. All right? Similarly, if I have a shifted delta function, which we need to use a lot, then I can just look at this integral. This is just going to sift out the value at x naught, right? So all I do is I plug in x naught for x, and I get e to the minus j 2 pi kx x naught. So we would say delta of x minus x naught goes to e to the minus j 2 pi kx x naught. Okay? So that's fairly simple. The next one's a slightly more complicated, which is the Fourier transform of rect of x, which comes in everywhere in medical imaging. So we know that this only has value from minus 1/2 to 1/2. So we can set the limits of integration from minus 1/2 to 1/2. It's equal to 1, so there's nothing here. So it's just the e to the minus j 2 pi kxx times 1, which is just itself. You just have to remember that the integral of an exponential is the exponential itself divided by its exponent. So you just plug that in here, and you get this. And then if you do a little bit of algebra, you end up with this interesting thing here, which is sine of pi kx over pi kx. Okay, and this function is so important that we give it its own name, which is we call it the sinc function. Okay, and this is something you'll want to get familiar with, and let's plot what it looks like. So first of all, what is sinc of 0? So sine of 0 is 0, and pi times kx is 0, so it's 0 over 0, right? So what thing from calculus should you now use? L'Hopital's rule, right? Everyone remember good old L'Hopital? Okay. So if you take the derivative of the top and the bottom, it turns out that you're going to get it's going to be 1. Okay. So it's going to be 1 there. Okay. So that's good. And then at what values is this function going to go to 0 now? Okay. It's going to, so sine of pi of 2, wait, let's see. Sine of pi is 0, right? Okay. So when kx is equal to 1, it's going to be 0. When kx is equal to 2, it's going to be 0, and so on and so forth. Okay? So the nice thing is this is a fairly easy function to think about. It's basically a sine function divided by pi kx. So you expect it to be a sine, but it's being divided by something that gets bigger as you go out. So it's going to look something like this. Okay? So it's like a decaying sine function. All right, so that's something that's going to come up everywhere when we're doing our imaging, so that's good to remember what that is. All right, so this is sine or sinc kx. Okay. So now let's think about what's the Fourier transform of 1. Okay, so we just plug in 1 here. 1 is valued from minus infinity to infinity. So we could just say, well, this is just equal to the minus e to the minus j 2 pi kx x over minus j 2 pi kx, right? From minus infinity to infinity. So that seems pretty simple, right? Okay, so what's e to the minus j 2 pi kx at infinity? Anyone? Okay, so one possibility is so let's say e to the minus j 2 pi kx times infinity. So one option is it's equal to 0. Okay, so anything else? Does everyone agree that it's equal to 0? So then it'd be 0 minus 0, right? Or 0 minus infinity, okay? All right, so it's actually not equal to 0, right? Because remember, this is just something like e to the j theta, right? So it's saying that I want e to the j of infinity, okay? And remember, theta is just the angle that this phasor is at, right? But that's not defined. So this is actually not defined at all, okay? So unfortunately, we really can't I don't want to spend time deriving this, but it turns out that the Fourier transform of 1 equals the delta function. And there's the proof here for those of you who want to go through sort of the generalized function thing. But for the purpose of this class, all you have to remember is that 1 goes to the delta function. Okay? Which is nice because remember we already had delta of x went to 1. Okay? So we're already seeing something called duality, which is if you know the Fourier transform one way, you can sort of know what it is for something that's similar. Okay? And similarly, these Fourier transforms here, if I take these things here, which would also blow up, it ends up being, this is saying that this is a spatial frequency of k naught. Okay? So this is a complex exponential with a frequency of k naught. So then it sort of makes sense that when we represent it in k space, it should just have something at k naught, right? If its frequency is k naught, then let's just, it should be represented by a delta function with a value only at k naught. Similarly, this guy here, cosine is e to the j 2 pi k naught x plus e to the minus j 2 pi k naught x over 2. There's a minus sign here. Okay, so this is going to have something at k naught and something at minus k naught. Okay, so then this is going to be, its Fourier transform is going to look like this. It's going to have something at k naught, something at minus k naught, and 1/2 and 1/2. Okay, because of this 1/2 factor. All right. So it's useful to know that complex exponentials go to Dirac delta functions. Basically, they're telling you what frequency they're at. Okay, so the way to think about it is look at the frequency, figure out what the frequency of the thing is, and then just put a delta function at that frequency. So in terms of thinking about it, it's fairly straightforward. For sine, there's just this 1 over 2j because the sine is, when you expand it, it's got a 2j in it. And there's also this minus sign. Okay. So these are examples of duality, which means that, for example, we said that delta of x goes to 1, and therefore I know that 1 goes to delta of kx. Sorry, delta. Let's erase that. So this is defined mathematically as this. If you know the Fourier transform one way, you can sort of guess. So this goes to 1. So I know that that's true, then I can sort of know that 1 goes to that. And so that's an example here where I know the Fourier transform of this, the delta function at a. So therefore, I know that the Fourier transform of this, which looks like this except the kx is replaced by x, should have similar form, but there's going to be generally a plus or minus sign that you have to take care of. Okay? So just sort of, today we're just giving you a lot of different facts. We'll review these as we go along, but just so you know what that is. So the biggest application of duality, or my favorite one, is this one. What is the Fourier transform of the sinc function? Okay? So those of you who have a lot of time on your hands may wish to evaluate this integral, sine pi x over pi x, e to the minus j 2 pi kx x dx. And even if you're a whiz at calculus, this is probably going to still take you like 5 or 10 minutes. It would probably take me, I'd have to Google how to do like differentiation by parts again and all that stuff. So it'd probably take me an hour or more. Okay? So that's not how I want to spend the next hour. So I'm going to be lazy and say, well, let's use duality. I already know that rect of x goes to sinc of kx, right? And those are both symmetric functions, so I don't have to worry about minus signs. So therefore, I can say, well, you know, actually then sinc of x must just go to rect of kx. And that's all you need to do. Okay, so that's the most useful duality to remember probably because it's the hardest to derive, which is rect goes to sinc and sinc goes to rect. Okay, so that's good to remember. Okay, now let's talk about the 2D Fourier transform. It's basically the extension of the 1D to multiple dimensions. So instead of g of x, we've got g of xy, and now we've got kx and ky. Okay, there's a minus sign here. When we do the inverse Fourier transform, there's no minus sign, but the form is identical. Okay, so once again, we have this beautiful symmetry of the Fourier and the inverse Fourier transform. So the interpretation here gets a little more complicated though, which is now we've got e to the j 2 pi kx x plus kyy, and so that's going to be a cosine of this 2 pi kx x plus kyy plus a j sine 2 pi kx x plus kyy. Okay? So let's look at what these things look like. So cosine 2 pi kx x, remember we're purely on the kx axis, and so now we see that this is a function of x, right? Okay, and so this is purely a function of x, and so this is representing my vertical stripes. Okay, so cosine 2 pi kxx is vertical stripes. Okay, similarly here I have the y-axis. If I have cosine 2 pi kyy, it's only a function of y. It's only going to vary in the y direction, and so this component would give me, if I only have the ky, it's only going to give me something looking like that. All right, so that matches what we talked about when we were doing sort of hand waving before. Now if I have both of them together, then it turns out I'm going to have variation in both x and y, because this depends on both x and y. Okay, where the spacing here is 1 over kx, and the spacing here is 1 over ky. Okay, and it turns out mathematically you can show then that space, this spacing here, is just 1 over square root of kx squared plus ky squared. So this is the proof here, but you know, I hate remembering things that are hard to remember, so I like to come up with easy things to remember. So the way I remember this is if I'm at some point in k-space, kx, ky, right, then I just think about the magnitude of this vector. So the magnitude of that vector is just kx squared plus ky squared. Okay, so therefore this, anything off diagonal, just has a spatial frequency of 1 over that. So this would correspond to a period, sorry, it's just 1 over the spatial frequency is just equal to 1 over kx squared plus ky squared. Okay? And it's also at this angle theta. And so this angle theta turns out to be, all this math is showing is basically just saying that then these stripes will be perpendicular, so that will be at that angle theta. Okay, so that's all this math says. This is here if you want to go through it, but this is sort of the picture I keep in my mind if I ever get confused. All right. Okay, so let's talk a little bit about what we do in the 2D transform. So in the 2D transform, let's say I want to compute the value of the Fourier transform at this spot. What I do is I take my object, I multiply it by some spatial pattern like that, okay, with the right frequency. So this has got 1 over kx, and then I integrate the whole thing. And that, the value of this integral is the value of the brightness of at that spot in k-space. Similarly, if I'm out here in k-space, now I just use a different pattern. I use the same object. The object is the same, but now I use a different pattern. I multiply them by each other, and then I integrate the whole thing, and I put that value over there. So that's what the Fourier transform is. And we will probably have some exercises later on in the quarter where we actually do this with MATLAB, but for now, I'm just throwing out what you're going to be doing. And the cool thing is that this whole operation is what an MRI system does. And the way it does the integral is it simply has a coil that just receives the signal and just adds them all up. Okay? So the cool thing is all this stuff that seems very theoretical is exactly happening every time we put someone in an MRI system. Okay? It's actually taking my object, multiplying it by these patterns, and then just summing it up. All right? Okay. So in the last 10 minutes, we're just going to cover a few of the sort of properties. We probably won't get through all of them, but at least cover some of them. The first thing is understanding separable functions. So for example, a function is separable if it's a function of x and y, but can be written as the product of a function in x and a function of y. Okay? And it turns out if a function is separable, then its Fourier transform it can be written as just the Fourier transform in the kx direction times the Fourier transform in the ky direction. Okay? So a good example of this is if I give you something like this. So that's just this two-dimensional rect function here. Okay? So this is rect of xy equals rect of x times rect of y. Okay? And this is obviously a separable function. So I can just take the Fourier transform of the rect of x, so that's sinc kx, and multiply it by the Fourier transform of the ky of sinc ky. Okay? So I don't have to do any math. I can just write down the Fourier transform by inspection. And this is really useful because this basically becomes a point spread function that we're going to see a lot. So this is my two-dimensional rect function here, and this is its Fourier transform. And we're going to see this happening a lot in our data. Okay? And the reason why is because if we say we're only going to collect data up to a certain frequency, it's essentially just multiplying the data by this rect function and saying everything else is 0. And anytime we do that, we're going to find out that our impulse response has this sinc function. Okay? Okay, so this is a example. So let's see. Yeah, so let's go through this. So the question is this function separable? Okay, so go ahead and take a minute and I'll put up the poll and see if you think that this function, tell me whether you think this function is separable or not. So this is just yes, no. You don't have to enter your names or not. Okay. Feel free to talk to your neighbor. You can certainly collaborate on this. Okay, so let's take a look at this. It's basically 85 yes, 15 no. Okay, so so let's write this out. So this can be written as e to the minus j 2 pi 8x times e to the minus j 2 pi 9y, right? Times sine 28 pi x, right? So this is clearly separable because we could write it as, we can group these two terms together. These are a function of x, and then it's multiplied by a function of y. Okay, so that's separable. Okay, but now if we do the Fourier transform of this, let's actually go through the Fourier transform of this. So the Fourier transform of this, let's think about this. This has a spatial frequency of 9, right? Because it's like 2 pi spatial frequency times y. So the Fourier transform of this is just going to be delta ky minus 9. Okay, so that's all that is. Now this part here, this is a function of x, this is a function of x, so we can't just multiply those Fourier transforms by each other. We need to expand this out. So let's do that. That's e to the minus j 2 pi 8x times e to the minus, let's say, plus j 28 pi x minus e to the minus j 28 pi x over 2j, right? Okay. And then think about this. This is 28 pi, but we'd like to write it as 2 pi. So it's like 2 pi times 14x or something like that. Okay. So we'll want to rewrite that. So we can think about this. So let's think about e to the minus j 2 pi 8x times e to the j 28. That first term is going to give us e to the minus j 2 pi. It's 14 minus 8, so it's going to be plus 6x, right, over 2j, minus e, so now we've got, this is 2 pi 14x, and it's minus, so it's going to be minus 22, right? So it's going to be e to the minus j 2 pi 22x over 2j. Okay, everyone see that? And so now this spatial frequency, there's a plus here, and so this is going to be at kx equals minus 6. There's a minus sign here, so this is going to be at kx equals plus 22. Okay, so for this one, we're going to end up with the Fourier transform is going to have a Dirac delta of kx plus 6 over 2j minus Dirac delta kx minus 22 over 2j. Okay? So that would be the answer for that one. Okay? So this is actually probably a little more complicated than we're going to get. This was, but it's certainly, we're not going to ask you to do anything more complicated than this for this class. So really what we're going to focus more on is taking very simple things and combining them. So this is about as sort of messy as it will get. All right. So yeah, so let's do a couple more examples. So the delta function of a two-dimensional Dirac delta. So this is the Fourier so the two-dimensional Dirac delta, that can be written as the Fourier transform of two one-dimensional Dirac deltas. So the good thing is even in 2D, we still have this delta x, y going to 1. Okay. But if we imagine a one-dimensional function, it's sort of interesting because this delta x is actually equal to delta x times 1. Okay. So if we look at its Fourier transform, we need the Fourier transform of this, which is just 1, multiplied by the Fourier transform of this. This is sort of 1 in the y dimension, so it's going to give me delta ky. And so then this is equal to delta of ky. Okay? So that's how we use separability. And the last thing we're going to end with today is talking about the center of K space. So the center of K space is where kx equals 0. Okay? And so if I plug in 0 here, it's just going to give me 1. So then I just have this integral here, the integral of gx dx from I sub to infinity. So this is basically just the area of my function. Okay? So that's why in general when we look at medical images, they tend to have a non-zero area, and generally the integral of that image tends to be the biggest number. And so typically for most medical images, the center of K space is always going to be the biggest, and then it's sort of going to drop off from there. Okay, so that's an important thing to know. It's basically proportional to the mean value of your function since it's the area. Okay, so let's stop there for today. The book has some basic Fourier transform pairs. We didn't really get into some of the properties, so we'll have to pick up on that in a later lecture. And then if you have questions about the homework or the lecture, I'm here for office hours.